So a statement from the first law of this, okay, if you say, okay, Q system equals Q surroundings, again, you got a negative on one side as a statement of the first law. So here's your first law again. If you, again, how many different ways can you state the first law? There is no free lunch, energy is conserved, right? Negative delta E system equals positive delta E surroundings. You got to designate system and surroundings. Here's another way to say it. Negative Q system equals positive Q surroundings. Okay, and if you take the MCATs on both sides, you can get this equation. Negative M system, specific heat system, delta T of the system equals mass of the surroundings, specific heat of the surroundings, changing temperature of the surroundings. Okay, so again, this is another statement of the first law. So we've got like probably at least 10 different ways you can say the first law. Okay. What was that? You don't need to know all of them. I would just ask you for maybe two ways of saying it. Most people can come up with 2 ways. But I'm always pointing it out because that's just the big picture. Always think the first law. Okay. Here's a sample problem. A 21.5 gram cube of aluminum, initially at 37.2, is submerged into 109.6 grams of water at 11.4 degrees centigrade. What is the final temperature of both substances at thermal equilibrium? This is going to be fun. So there's 2 ways you can do it. You can plug in the numbers first and then try to manipulate things. I like to just manipulate the equation first and plug in the numbers. All right, so let's look at just manipulating this equation. Here we go, some algebra. Okay. So we take the first law, a negative M system, specific heat system, times TF minus T initial of the system. That's equal to the positive of the other side, mass of the surroundings, specific heat of the surroundings, times delta T of the surroundings. All right, so that's our first law. What can we take as our system? What can we take as our surroundings? What are we doing here? It says a cube of aluminum, okay, and is submerged into water. So what can we take as our system? We can take either the water or the aluminum. It actually doesn't matter which one we take. Okay, as long as we have a negative sign somewhere in here. But just out of convenience, I guess we can take the aluminum as the system since it's being dunked into the water, which could be construed as the surroundings. Okay, so we're going to change this now to negative M aluminum, C aluminum, T final, which we're going to say that's going to be the same at thermal equilibrium. This other side will be mass of water, specific heat of water, T final minus T initial for, water. Okay, so at equilibrium, this is the key idea here. At equilibrium, T final aluminum is equal to T final water. All right, that's the key idea here. So once these reach a thermal equilibrium, they're going to be the same temp. Okay. So everybody okay with this so far? Just the setup. So what do we have to solve for? We have to solve for TF, which are going to be the same value. So let's do that. Okay, so what we can do is, we can say, okay, we can do our distributive property on both sides. All right, so mass of aluminum times C aluminum times TF plus, and it's plus because it's negative times negative. All right, so this makes this a plus. Mass of aluminum, C aluminum, T initial aluminum. On the right side here, we got M water, C water, T final, minus M water, C water. Sounds like I'm saying seawater like the ocean, but it really it's specific heat of water. Okay, and then times T initial water. Okay. So where can we go from here to solve for TF? What I suggest is maybe get the TFs on one side and then everything else on the other. So let's go ahead and do that. So adding plus M aluminum, C aluminum, TF on the other side now, and then adding this on the other side still, we're going to get M aluminum, C aluminum, Ti aluminum, plus we're going to get M water, plus seawater plus our times T initial water. And on the other side we get plus M aluminum, C aluminum, TF, plus M water, C water, TF. So I just added this over there, and I added this over here. Now this should look like it's ready to happen, right? What could I do with the TF here? I can distribute it back out again, right? Factor it back out. So this is the same as saying TF times M aluminum, C aluminum, plus M water, C water. And now I can divide both sides by M aluminum, C aluminum, plus M water, C water. That gets rid of that, and it comes over here. All right. Okay, so now we're just going to plug in the numbers. So TF is equal to M aluminum, C aluminum, T initial aluminum, plus M water, C water, T initial water. All right, all of that is divided by this here, M aluminum plus boiling water, oh, excuse me. Okay, so TF, let's see, mass of aluminum is what? And now we can look at the numbers. All right, we got a 21.5 gram cube. We have specific heat of aluminum, which, let's see, on yours, did I write the, on your notes, are there the masses and specific heats listed on there? Yeah, 0.903 joules, so that's specific heat for aluminum, right? So joules per gram per degree C times the initial temp of aluminum, which was 37.2. Okay, plus mass of water, which was 109.6. Grams. 4.184 joules. All right, and then we have initial temp for water, which is 11.4. So the degrees and grams cancel on all these. On the bottom, you got still 21.5 grams. So on the bottom, the grams cancel, but the degrees Celsius don't cancel. Okay. So how do we know that what units are we looking for at the end? What is it asking us for? It's asking us for what is the final temperature, right? So we're looking for units of degrees Celsius, right? And they do indeed cancel. Because the units for the joules will cancel out on the bottom too. So joules divided by joules. All right, and then what you end up getting is degrees Celsius that come back on the top. So the answer ends up being 12.4 degrees Celsius. And does that answer make any sense? So if water was at 11.4, the aluminum was at 37.2, it's like dropping a hot cube into water instead of an ice cube. It's a hot cube. So would you expect the water to get warmer? The answer is yes, you would. So, any questions about thermal equilibrium? This is the hardest of the hard, like in terms of math. It's probably easier if I asked you a question to solve for the specific heat of one of them. That's a lot easier. But I figured I'd show you the hardest of the hard to, give you the hard. Then it's easier from there. In Chem 107, you should have done one of these. Do you remember? If not, then now you've seen it. Okay, so if there's any questions on thermal equilibrium, we shall head upstairs.